Hi, welcome to Math 150, Section 1, Lecture 24, we've decided 2021. So today we're going to continue our discussion on sequences and series. And so we are going to start the big slew of methods to determine when a sequence converges. Notice I'm not saying evaluate what it converges to. That is a much harder question. The easier question is just, does it converge? And then if it converges, there are often techniques you can do to numerically approximate it. I sent you some really fascinating videos on the sum of the reciprocals of the squares is pi squared over 6. And it turns out that this has a lot of amazing applications, but when you're summing a series, it's going to be very hard to see that it's converging to exactly pi squared over 6, as opposed to just something that's very close to that. Lurking in the background of everything we do is our favorite series or our favorite sequence. Which one is that? Which one do we like more than anything else? The geometric. So the geometric is our go-to. It is the easiest one for us to study and look at. And really what's going on with the ratio test and the root test is they are applying the geometric series under the hood. And they're calculating which geometric series to use in the comparisons. The comparison test is more like art. It's like looking at a quadratic polynomial and trying to see the roots. If you can just see the roots, that is the fastest way to factor the quadratic. But if the roots are very complicated, it's not going to be easy for you to just see them. Now, when you are taking Algebra 1, Algebra 2, do you think they're going to give you painful roots? Occasionally, because they want to make sure you know the quadratic formula, but a lot of times you'll be in a situation where you can just use inspection to find the roots. For a lot of problems, we can just use inspection to figure out, hey, let me compare it to this and see if that works. If you happen to choose a good comparison and it works, you're done. It doesn't matter how you found it. Or maybe it matters a little bit in case I give you a related problem in the future, or someone else gives you a related problem, and you want to be able to do this again and have another success. But for the specific problem, if you find a good sequence to compare it to, and you get it converges or diverges, you're done, you don't need to do anything else. The question becomes, how do you find a good comparison? How do you find a good sequence? And the ratio test, the root test, these are all trying to just automate that process for you. And if you calculate certain algebraic expressions, it will then give you the answer. So the first one is the ratio test. And so we have a sequence AN. And if you want, what can I assume about the terms AN if I'm going to apply the ratio test? Why not negative? What can I assume the terms AN are tending towards? 0. Why can I assume the terms are tending towards 0? We don't know if it converges or diverges. What happens if the terms aren't tending towards 0? What would be true about the sequence if the terms aren't going towards 0? What do we immediately know? It diverges. So when I'm trying to design the ratio test, if you want, you might as well just only apply the ratio test to a sequence whose terms are tending to 0. If the terms aren't tending towards 0, why bother with the ratio test? We already know it doesn't converge. Now, the ratio test still works in cases when the terms are not tending towards 0. But if you want in your mind, you can say, well, look, let me just quickly look at my go-to is going to be, do the terms tend to 0? If they don't, there's no need to do anything further. So we have a sequence AN. Often you can assume AN is going to 0, and if you want, you could even assume AN is greater than or equal to 0. Because if the terms are going to 0, if I want to know if the sequence converges, then we're talking about the sum. Then let me hold off on that for now. Let's just say the term's going to 0. We want to study the sum n goes from 0 to infinity of an. And we want to figure out, does this converge or diverge? And so we let rho equal the limit as n goes to infinity. And so what ratio do we look at for the ratio test? An plus 1 over an. Or do we look at the absolute value? You can do it several ways. You can look at this ratio and then look at the absolute value of rho, or you could just take the absolute value to begin with. Because what is the condition for convergence? When does it converge? If the absolute value of rho is less than 1. So when you're looking at this, you can either take this limit over here as stated, and then look at the absolute value of rho, or you could insert absolute values here. Doesn't really matter which way you do it. Does anybody have a preference one way or the other? Do you want to take the ratio and then take absolute values, or take absolute values to begin with? So let's take it to begin with. Now you can see why it doesn't matter if the terms are positive or negative. Because if the terms are negative, well, I'm computing a ratio and I only care about its absolute value. So I don't really care about the sign. So without loss of generality, I might as well assume the terms are non-negative. It's not going to really affect whether or not it's converging or diverging, because we're going to be comparing it to a geometric series. So it's actually not a big deal. What is the one thing that scares you right now when you see that ratio? So when you see this ratio, what worries you? I'm giving you an plus 1 divided by an. As soon as you see that, as soon as you hear a word, you should be afraid of something. Dividing by 0. Like, if I ever divide by 0, I'm in trouble. So we will assume an is equal to 0, but we'll assume that each an is greater than 0. So somebody give me a series that converges, an infinite sum that converges. Yes. Because we were talking about we might as well assume all the terms are positive. But if you want, you could do instead an not equal to 0. Either one of those is fine. So can somebody give me an example of a sequence of terms whose sum converges, other than this term that's all zeros? Good, well, yeah. So 1, 1/2, 1/4, 1/8. Right? And this sums to 2. Now, the way I've written this, there's a huge space between all the terms. What if I do the following? I'll put a 0 everywhere between the terms. Have I changed the sum? No. But if I try to use the ratio test, the limit won't exist, because I now have all these divisions by 0. So if I do something trivial like this, it's going to cause problems. So I will assume that my sequence does not have any 0 terms. Well, it's not really a big deal, because if you just remove any term from the sequence that's 0, you're not going to change the sum, because you're changing the sum by 0. So if rho is greater than 1, it diverges. If rho equals 1, no information. And if rho is less than 1, it converges. So this is the ratio test. So all we have to do is compute this one number, and that will tell us if the sequence, if the corresponding series to the sequence, if the sum of the terms converges, diverges, or if we're unfortunate and we have to do another test. And so the reason it works is it's essentially comparing AN to a geometric series. So I'm going to just give a quick sketch, not too rigorous. Do you want to do the case when it converges or diverges? What kind of mood are you in today? Converges. We're going to converge. So we will assume rho is less than 1. So what does it mean if the limit is less than 1? It means given any small epsilon greater than 0, for all n sufficiently big, we have rho is going to be less than 1 minus epsilon. So if you want, say rho equals 0.999, and then this is saying that eventually, I'm sorry, an plus 1 over an, sorry, will be less than 1 minus epsilon. So maybe 1 minus epsilon is 0.9999. Because if it's converging to 0.999, then eventually it's got to be less than 0.9999. Does that make sense? But because this limit eventually converges to rho, it's got to get really close to rho. So here is 1, here's rho equals 0.999, here's 0.9999. Since the limit exists for all n sufficiently large, the ratio has to be really close to rho, so it's going to be strictly less than this. So let's say this is true if n is greater than or equal to big N. Okay. So from this point onward in the sequence, the ratio of adjacent terms is at most 1 minus epsilon. So this tells us that a big N plus 1 is going to be less than 1 minus epsilon times an. Okay. And now, an plus 2 would be less than 1 minus epsilon times an plus 1. Just looking at the next term. But what do we know about an plus 1? It's less than 1 minus epsilon times an. So this would be less than 1 minus epsilon squared an. And if you continue, you get an plus 3 is less than 1 minus epsilon an plus 2. So it's less than 1 minus epsilon cubed an. And so you see from big N onward, each term is at most 1 minus epsilon times the previous. It's bounded by a geometric series. So now you can do a comparison test. If I sum all of these, the absolute value of an plus an plus 1 plus an plus 2 is going to be strictly less than 1 plus 1 minus epsilon plus 1 minus epsilon squared times an. And I'm just replacing term by term with something that's logical. And that's how you will get convergence. So this is a quick sketch of the proof of the ratio test. If you wanted to have divergence, you would have rho is greater than 1. So eventually, this limit would be strictly greater than 1 plus epsilon to some positive epsilon. You'd be able to show that the corresponding sum is too large. Okay, so this is the ratio test. So now the question is, how do we use it in practice? We have to be able to compute this limit. So let's start off with an easy limit. Let's let an be 1 over n factorial. N factorial is n minus 1, 3 times 2 times 1, and 0 factorial is set to be 1. So n factorial is the number of ways to order n objects with order matters. So you have, say, 5 people. There's 5 people who could be president, and then of the remaining 4 people, you then choose 4 to be vice president, 1 of the 4 to be vice president, and 1 of the remaining 3 to be treasurer, then secretary, and then so on. So if we want to calculate rho, it would be the limit as n goes to infinity of an plus 1 over an. And when I do these problems, I always like to start off by explicitly writing what I'm calculating. I'm calculating rho equals this. And now I substitute. So I would get the limit as n goes to infinity of 1 over n plus 1 factorial divided by 1 over n factorial. Well, this is the same as the limit as n goes to infinity of 1 over n plus 1 factorial times n factorial. Okay. What's n factorial divided by n plus 1 factorial? It's 1 over n plus 1. This is the same as the limit as n goes to infinity of n factorial upstairs, and n plus 1 factorial is n plus 1 times n minus 1 times n. It's just n plus 1 times n factorial. Well, this is the same as the limit as n goes to infinity of 1 over n plus 1. And as n goes to infinity, what does this go to? 0. So this converges. So this is already a great example. We could have done this with a comparison test, and I'll do it with a comparison test in a moment. I want to first do a generalization of this, where it's really nice to be at the blackboard. So instead of doing an is 1 over n factorial, I'm going to do x to the nth power over n factorial. And let's just see how much that changes. If x is a large number, what happens to x to the n? What does it look like if x is, say, 2 or 4 or 10? What happens to x to the n? It gets really large. But n factorial is also getting really large. And so the question is, does n factorial get large so fast that it's going to dwarf the x to the n? The answer is yes. So when I go through this, instead of having 1, I'm now going to have x to the n plus 1. I'll have x to the n down here. So we have x to the n plus 1 and x over here. So just be x times that. What can I do to this limit with the x? What can I do to the x? Remember, x is fixed. So what can I do to a limit if I multiply the inside by a fixed number? Yeah, I could pull out the x. Or I could leave the x here. It doesn't matter. I could pull it out or I could leave it here. But because x is fixed, as n goes to infinity, it's still going to go to 0. So this converges. So in particular, the sum n goes from 0 to infinity of x to the n over n factorial converges for all x. And this is just a function e of x. So this is one of the most important sequences of series. Yes?
Did you drop the x to the n?
Oh, yes, there should be an n over there. Thank you. I did the algebra as if it was x to the n, but I did not write it on the board. So this is, again, a really nice application of the ratio test. We now have that this sequence converges, and converges for all values of x. We could have done this without using the ratio test. And if we just looked at an is 1 over n factorial, this is going to be, let's equal to 1 over n times n minus 1. Does everyone agree that when n is large, this is going to be less than 1 over n minus 1? Because I'm not including the n minus 2, n minus 3, n minus 4. There's a lot more terms. So this is going to be less than if you do a little bit of algebra, 4 over n squared if n is large. Or if you don't want to do that, a more interesting one is this is going to be less than 1 over n minus 1 squared. I make it larger if I replace n with something small. What series could I compare this to now? We have each term an is at most 1 over n minus 1 squared. What could I compare that to? We've done this sequence already. One over n squared. It's just shifting everything by 1. So if I rename everything, if I just shift everything over by 1, it's not going to affect whether or not it converges. So I can compare this to 1 over n squared. Which proof do you think is harder? Doing the algebraic insights like this to show that an is less than 1 over n minus 1 squared, and then compare it with 1 over the squares, or just applying the ratio test and calculating that limit and seeing that limit is 0. For me, I think the ratio test is easy. Because here, I had to think, well, actually, n factorial, it's a huge product. If I only take a couple of factors, it's going to be an upper bound. And I can do some algebra shifts to either 4 over n squared or 1 over n minus 1 squared, and I can compare it. I can do it with the comparison test. I've also been teaching this class since before you were born. I started teaching this class in the late 90s. When you have this many years of experience, we're not talking decades of experience, I should be able to quickly look at these and know which comparison to use. The more times you do it, the easier it becomes. When you're starting out, the ratio test and the root test are more like the quadratic formula. They're more straightforward in application. I think they're a little bit easier to apply than the comparison test, because for the comparison test, you've got to figure out what to compare it to. But if you can figure out what to compare it to, you don't have to do the algebra of the limits. And so it does have advantages. So one of the questions that was asked is, well, what should our go-to be? I think step 1 is check and see, do the terms tend to 0? If the terms do not tend to 0, then you're done. Then if the terms tend to 0, what do we do? Well, if the terms tend to 0, take a quick look at it and see if divine inspiration hits. And if you look at it and you see a natural candidate to try it. And if it works, great, you're done. If it doesn't work, maybe try something else. But if you try a few things and nothing is working, then go to the ratio test. If the ratio test is not working, then go to the root test. Okay. Any other questions on this example? Okay, let me give you another example that's a little bit harsh. An is 2 to the n plus the square root of n plus 4 divided by the square root of n factorial. Okay? This should look a little painful. If it's not, I'm failing. Does this look pleasant? So one question is, can you look at this and try to maybe simplify the algebra a little? What is your intuition? Do you think it converges or diverges? So you think this diverges. Why do you think it diverges? So we have the 2 to the n in the numerator. Which wins, 2 to the n or the square root of n plus 4? When n gets really, really large, which is going faster? 2 to the n or the square root of n plus 4? I'm sorry? 2 to the n. How large? Can you give me an upper bound for the square root of n plus 4? Yeah, it's at most n plus 4. If I increased n to n plus 4, then this would be the square root of n plus 4 squared. So this is going to be at most n plus 4. And we know that 2 to the n goes much faster than n. So we know that for very large values of n, this would be less than or equal to, if you want, say, 3 times 2 to the n over the square root of n factorial. Or if you want to make the algebra a little bit easier, that's 4. Doesn't really matter. When n gets really, really large, the numerator is really at most 4 times 2. If I think the sum converges, all I have to do is show that the limit is going to some row that's less than 1. I don't have to compute what the actual value is. So rather than working with this, do you really want to look at an plus 1 divided by an for this and try to do the algebra? I'm just trying to simplify things a little bit. I'm trying to find a new sequence that's larger than this from some point onward, and then show that that sum converges. And I'm going to use the sandwich theorem or the comparison test. This is going to be a little bit easier to do. If you are really good, you can see that this is going to be 4 times the square root of what divided by n factorial. So the square root of what equals 2 to the n? You need to remember your exponent box. So we will do a review of exponents and logarithms on Monday. I think that will be a useful class. What has square root 2 to the n? So I want y equal the square root of 2 to the n. I'm sorry. I want the square root of y equal 2 to the n. So how would you solve the square root of y equals 2 to the n? Square both sides, so you get y equals what? 2 to the 2n or 4 to the n. We just proved a moment ago that x to the n over n factorial converges, right? The only difference now is we have a square root. So it would be the same algebra as before, except now we get a 1 over square root of n plus 1 rather than a n plus 1. And so the algebra is going to be very similar from this point on. So a lot of times when you're trying to do the ratio test or the loop test, rather than doing the sequence you're given, if you believe it converges, what you can often do is find a series where the terms are a little bit larger, and it will be easier to do the algebra. If you think it diverges, find a series that's a little bit smaller, where it will be easy to do the algebra. Now, if we did this, and we got rho is less than 1, then we win. What if we got rho is greater than 1? Would we know that the original series diverges if we get rho is greater than 1? So you shake your head, why not?
Because we're comparing like a function is greater.
Well, we're comparing to something that's greater. So we would know that this sum, the sum of these terms, would diverge if rho is greater than 1. That's great, but that doesn't tell us that the original sequence. If I give you an is 1 over n factorial, that's less than 1 over n, and the sum of 1 over n diverges, wonderful. But that doesn't give me any information about 1 over n factorial. The comparison test doesn't work that way. If you have something that diverges, it gives you information about series that are larger. It doesn't give you any information about series that are smaller. If you have something that converges, it gives you information about sums that are smaller, but not about sums that are larger. So over here, if I do the algebra like this, I can reduce this to a previously solved problem, which is wonderful. The difficulty is that I have to see how to do the algebra. So what we could do is we could try to do the limit directly. And so if you look at rho equals the limit as n goes to infinity of an plus 1 over an, by writing it like this, you make it very easy for whoever's looking at your paper to understand what you're doing. Oh, I'm doing the ratio test. Got it. I see what's going on. Don't just start writing math on the paper and expect me to follow what you're doing. Do you think I can look at your paper and figure out what you meant to do? Of course, right? You should have faith in me. But I can't do that. I am not supposed to think about what was your intent. I'm not supposed to think, how can I interpret this? Okay, so remember, when you are writing things down, you have to put down enough detail so I know what you're doing. Similarly, how many answers should there be on a problem? 1. There are times when students will have multiple answers and one of them is correct. It has to be clear which is the answer you want. And so when you write something like this, it makes it much easier to grade. It makes it much easier for you to go through the algebra and minimize your chance of making a mistake. I'm now clearly using this formula, and now I'm going to substitute in. And now the nightmare begins. It's the limit as it goes to infinity of an plus 1. It's going to be 2 to the n plus 1 plus the square root of n plus 1, n plus 4 over the square root of n plus 1 factorial. And then to save time, I'm going to take the an down here and just flip it. It'll be the square root of n factorial over 2 to the n, oh, this should be n plus 5. 2 to the n plus the square root of n plus 4. And so now I want to calculate this limit. So it's the limit as n goes to infinity. Now, the square root of n factorial divided by the square root of n plus 1 factorial, that's pretty easy. That's just going to be 1 over square root of n plus 1. And then I have a 2 to the n plus 1 plus the square root of n plus 1, n plus 5 over 2 to the n plus the square root of n plus 4. So when I look at this should remind you a little bit of when we had ratios of polynomials and we looked at what was going on and we pulled out the highest degree on both the numerator and the denominator. So I would pull out a 2 to the n from the denominator, a 2 to the n plus 1 from the numerator, and that would give me just a 2. So this would just be the limit as n goes to infinity of 2 over the square root of n plus 1. And now I'm going to pull out 2 to the n plus 1. So I have 1 plus the square root of n plus 1, n plus 5 over 2 to the n plus 1. And down below I pull out the 2 to the n, it's 1 plus the square root of n plus 4 over 2 to the n. The limit of a product is the product of the limits. So long as both limits are finite, if one limit is infinity and one limit is 0, then you don't get to say that. But as long as both limits are finite, the limit of a product is the product of the limits. What's the limit of 2 over square root of n plus 1? This piece goes to 0. And what about this piece? What does this piece go to? And it gets really, really large. What does the numerator go to? 1. And what does the denominator go to? 1. So this is really typical of a lot of ratio problems. We don't have to calculate the limit precisely. We just need to get we just need to be able to tell, are you less than 1? Are you equal to 1? Are you greater than 1? As long as it's less than 1, I don't care what value it is less than 1. Now, if I wanted to know how quickly it converges, the smaller row is, the faster it converges. The larger row is, the faster it diverges. But if I just want to know, does it converge or diverge, I just need to know, is it less than 1, is it greater than 1? And so over here, I don't need to do the algebra that well, I just need to do enough to tell me that this ratio is going to go, this whole ratio is going to go to 0. So again, when you're doing these problems, the more problems you do, the easier it's going to become. You'll start to get used to these different techniques. It all comes down to knowing algebra. Your Algebra 1, Algebra 2 are probably the most important classes you take in high school, but it's not really emphasized at the time. All the math later really uses those in a fundamental way. And this is why on Monday I'm going to review logarithm laws, exponent laws, and just give a quick review of stuff like that. Okay, any questions on this calculation? So this is another example of how we can use the ratio test. So the ratio test is extremely powerful. Is there anything the ratio test can't do? Can anybody give me a sequence, where the ratio test cannot tell me if the corresponding sum converges or diverges? AN equals. Where does the ratio test fail? I need something that has a limit of 1. Come on. So 1 over n, or more generally, 1 over n to the p. So n is the negative p, 1 over n to the p, however you want to write it. So in calculus, they call this a p series. And it converges if p is greater than 1, it diverges if p is less than 1. So it converges if p is greater than 1, diverges if p is less than 1. And so we actually showed this convergence and divergence. Let's apply the ratio test. So rho equals the limit as n goes to infinity of an plus 1 over an. It's the limit as n goes to infinity of 1 over n plus 1 to the p divided by 1 over n to the p. Okay. This is the limit as n goes to infinity of n to the p divided by n plus 1 to the p, or it's the limit as n goes to infinity of n over n plus 1 all to the p. But p is fixed. So what do you think this limit should equal? So what should this limit equal? What's the easiest value of p to start with? Give me a value of p that we should look at. 1. So if p equals 1, we have the limit as n goes to infinity of n divided by n plus 1. What's that limit going to be? One. And so, 1/2, 2/3, 3/4, 5/6, 99 100ths. You basically lost one game in all of your matches. As you play more and more games, if you've only lost one game, your revenue is getting closer and closer and closer to 100%. There'll always be a little bit less, but you're essentially playing perfect. So for that one mistake, And so as n gets very, very large, this gets as close as you want to 1 from below, its limit is going to be 1. And so, unfortunately, the ratio test gives us no information when p equals 1. What you want to say is that the limit of this to the pth power is the same as the pth power of the limit. If p is an integer, that's not so bad. If p is not an integer, it's a little bit harder. But if you're willing to just accept that, it's not so bad. So let me quickly show what to do if p is not an integer. But if you're willing to accept that statement, then we're done immediately, because now we know that rho is just always equal to 1. So again, if you're trying to do some algebra, it's the same as the limit as n goes to infinity. There are two different ways to do this. All right, n plus 1 minus 1 over n plus 1. If I really change the numerator, I can write this as the limit as n goes to infinity of n plus 1 over n plus 1 minus 1 over n plus 1 to the p. This is the same as the limit as n goes to infinity of 1 minus 1 over n plus 1 to the p. And here the difference is p is fixed. So because p is fixed, p might be 100, 1,000, whatever, it's a fixed number. I can make this as close to 1 as I want by taking n to be really, really large. And since I'm raising it to only a finite power, it's not going to get that much smaller. Have you seen this alternate definition for e to the x? E to the x is the limit as n goes to infinity of 1 plus x over n to the n. This is the compound interest formula for e to the x. Have you seen this? How many of you have seen this formula? So, a few people. So for those of you who've seen this, this is kind of like taking x equals -1. The difference is here, I'm raising it to an arbitrary power, to the same power I'm dividing x by. Whereas here, it's a fixed power. And so, because that power is fixed, it's going to limit how much smaller. But if you want, if you do p for a specific integer, this is already enough to show the problems to show that the ratio test can't resolve it. So the ratio test is not powerful enough to do all the stuff we want to do. So in the next class, I think we'll probably be doing the root test. And then we also have the integral test. For the root test, it's very similar to the ratio test where you have a specific formula, you compute the nth root of an, and you see what does that converge to. The integral test is a little bit harder. You have to find a function, and then you integrate that function. Almost always, the way you find the function is you take your sequence an and you replace n with x. That works almost every single time. And if you replace n with x and you try that almost always works. And because of that, the integral test is not too bad to use. Because for the most part, you know what to try. Right. Any other questions on stuff we've done today? So again, the more examples you do, the easier it's going to be. Go through problems like a list. Start having a collection of sequences and series that you know. 1 over n to the p converges if p is greater than 1, diverges otherwise. That's a great example to use for comparison. R to the n converges if R is less than 1 in absolute value, diverges if R is greater than or equal to 1 in absolute value. The ratio test gives information if rho is greater than 1 or if rho is less than 1. It gives no information if rho equals 1. And just when you get a sequence of series, just go through, but always, always, always go for the low-hanging fruit first. Before you try to calculate using any of these tests, what's the first thing you should do when you look at the series? Yeah, do the terms converge to 0? If the terms don't converge to 0, there's no need to go through all this painful algebra. So again, in any test or homework in a class like multivariable calculus, it shouldn't be a truly painful problem. There should be a path through it, and that should be a real help as you're doing the problems. If any of you ever did math competitions in high school, there has to be a nice way of doing these problems in a short amount of time. There has to be a trick. And once you know that, it really impacts how you attack the problems. Is you're not going to have pages and pages and pages of calculations. One of my thesis students years ago, I think, had the best opening of a thesis defense in Williams history. Is he starts off with an equation that fills the entire piece of paper in small font. This expression here equals this expression here. So for those of you in the audience, it may be hard to understand what's going on. Let me expand it out. And he expands the left-hand side, and it takes 10 to 20 pages to expand them to the left-hand side. Then you have a slide that says equals, and you have another 10 or 20 pages of expanding the right-hand side. And you now have to show all the corresponding terms are the same. You have to come up with a good way to go through these calculations. And this was doing the case of 4, and it gets even worse as you go higher up. And you need a good path through all the algebra, or you're going to be overwhelmed. Now, what's nice in a class like this, you should not be overwhelmed. If it's an extra credit problem, maybe. Maybe for something like that, it could be truly painful. But if you're having something where it's not working, this is a signal that you might have done something wrong. You might have made an algebra mistake, or you might have missed an easier way to look at it. And think of our favorite New England transcendentalist writer, Thoreau. And actually, my wife and I were hiking this weekend in South County, and we actually found a bench where one of Thoreau's sayings was sculpted into it. Simplify, simplify. Before you start doing the calculations, step back and say, rather than looking at this problem, is there a related problem that I can do that would be easier? And if you think something converges, all right, I might have a little wiggle room to play with. If I think it converges, let me make things a little bit larger if it's going to simplify the algebra. And then if it still converges, great, I win. Or if I think things diverge, let me shrink things a little bit and see if that simplifies the algebra. And if that does, great, I win. All right, have a good rest of the day. Enjoy the weather.